Hello students, welcome to ECEN221 lab for signals and systems. Today we will start project 1, the first lab, and the purpose of this project is to review some properties of basic continuous time signals and explore how MATLAB can be used to visualize these signals. The exercises focus primarily on the following types of signals: real exponential signals, sinusoid signals, harmonically related periodic signals. These signals, if you remember, we studied in the theoretical part in ECN 220 in chapter 1. So to have more knowledge about these signals, you can go and refer to the lecture for this chapter. Okay, in addition to exploring the properties of these signals, this project will also provide an opportunity to review the use of script files in MATLAB. That means how we can make script files in MATLAB and how we can execute different kinds of, for example, functions and make script files for signals, to plot signals, to construct signals, to analyze signals, and so on. The lab report submission should include all theoretical paperwork and also any MATLAB commands, script files, all the results, including figures and discussions. Discussions are very important because from the discussions we can know that the student gets the knowledge for that lab project by, for example, visualizing the signals in the graph. You can talk about the behavior of the signals, the property of the signals, and what is the use of, for example, constructing the signals in MATLAB and so on. And for more detailed explanation, please refer to the lab manual posted in Blackboard. Your work will be to write the MATLAB script files to generate and plot different signals as described in the lab manual. Okay, the first part is constructing sinusoidal signals. Sinusoidal signals are signals, as you know, they are sine and cosine form. For example, if I have a signal P of t, so the variable is P and the independent variable is t and the dependent variable is P. P is a function of t, that means is equal to cosine of omega naught t plus theta. This is the general form. For example, for cosine signal, omega naught and theta are real parameters. What is omega naught? Omega naught is 2 pi over fundamental period. It is called the angular frequency in radians per second. And t is called the fundamental period. And from this also we have the frequency f naught. F naught is 1 over t, is the frequency in cycles per second or hertz. And theta is phase shift in radians or degrees. Okay, so this is the general form of the cosine signal. And for this signal we have, for example, here 3 types of signals. You will define a vector of time using the MATLAB command. For example, here I have time t starting from 0 until 10, and 0.01 is the time step. So how we define it? T is equal to 0 initial time, colon 0.01 and colon and 10. And we generate this time vector and we plot by calling the cosine and the sine function. Very easy, this one. And for different types of omega naught and theta. The purpose is to compare the different signals that you plotted using the MATLAB command. How you plot them? You will use the subplot command to place three plots on the same figure, but with three rows, having three different axes. So the first row will be the signal P1 of t, okay, as a function of time. And the second row will be the signal P2 of t as a function of time. And the third row will be P3 of t as a function of time. And of course, you will have x, y labels. You give x label, y label. X label is time, of course, and y label is the amplitude of the signal. And also, you can have legend, of course, you can put legends, and you can use different colors for plotting the signals. So here is, for example, one example here. This is omega naught is equal to 2 pi. This is a script file, for example. You can run it in the MATLAB command window, or you can construct a small script file, and you can call in the command window the script file and run it, and you will get the result. Here, for example, clear all means clear all variables. This is just to avoid confusion if there are some variables in the workspace, so that you remove all the variables. You start with fresh. That means omega naught is 2 times pi here. Pi is already MATLAB knows what pi means, and t is equal to 2 pi over omega naught. This is a relation between the period and omega naught. It comes from this relation, omega naught to pi over t, and t is 2 pi over omega naught, and the maximum time, for example, 2 times t. That means I want to plot two periods, and the time step is 0.01, because here we said the time step is 0.01, and we have the signal from 0 until t max. The maximum time is two periods, and theta pi over 4, and then I call the function, this is my signal, x of t, I call it x of t, 10 times, 10 is the amplitude, the maximum value, times, in MATLAB how you write it, with a star sign here, star, sine of, now this is a function, you are calling sine, MATLAB knows sine, so omega naught times t plus omega naught, you defined it here, times t plus theta, T-H-E-T, here I defined it as theta, and then you plot t, x, t. The x-axis will be the time, and the y-axis will be the signal amplitude. And you make grid on means make square grid for the plot, and you give the x label time, you label the x-axis as time, you label the y-axis as the signal amplitude. So let's go and see here in MATLAB how this can be done. So I already have MATLAB here, and before I run this program, I just would like to explain. This is a window of MATLAB. When you open the MATLAB application, you have this. In this part, it shows you the current folder. Folder means the folder you are working. For example, here, how I know my folder or directory, a command called pwd tells me where I am. E, and I have here one directory, and then AURAC, MATLAB, and this is my directory. You can construct your own folder or directory, so you can go to lab 221. This is lab 221, for example, for my directory. Okay, so if I see it here, exactly this is what it means: E, AURAC, MATLAB lab 221. Okay. By the way, if you are in a different folder, how you go to that particular folder, you say cd. For example, if I want to go to this folder, I call cd, and cd means change my folder, change my directory, cd to this. Then I will be in that folder. That means change my directory to, so you should give exactly where you are. Here, for example, my root directory is E, and then I have another folder here, and then I have AURAC, then MATLAB, and then Lab 221. So based on your folder where you would like to work, you can create your own folder and you say change CD to that folder. Okay, by using that, you can go to that folder. Sometimes you can put also apostrophe if there is a gap between when you create the folder. If there is some gap, then you can put apostrophe like this, and then you can do like that. Okay. Now this is the folder. And what about this part? This part is called workspace. The workspace consists of all variables that you are working with. Here, for example, because I am going to this folder, my variable is answer, and this is a folder. Okay, if there are any variables, it will come. For example, here, if I say x is equal to 5, y is equal to 10, and enter. See, now x, I see them here. X is equal to 5, y is equal to 10. This is the name of the variable, and this is the value of the variable. And if I say z is equal to, for example, x plus y, I am adding, I will get 15. So another variable is created here, 15. Okay, this is called the workspace. So if I make a vector, for example, another vector, let's say, let me call it A. This is my vector, and I start with 1, and my time step is 2, and I go until, for example, 11, my maximum. So if you don't put semicolon, you will not see the results in the command window. This is called the command window. This part is the command window. So if I remove the semicolon, I can see my elements for the vector. So the vector starts from 1. After 1, if my time step is 2, 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 2, 9. 9 plus 2, 11. So my time step is 2. So MATLAB will make a vector with initial element 1, final element 11, and time step 2. Okay, so you can create any vector by this way. If I say, for example, if I say 10, my time step is 10, and I would like to go from 0 until 100. Okay, so it will list for me all the elements between 1 and 100. See, between 0 and 100. So 0, and then because I start from 0, then 10, 20, 30, 40, 50, until 100. This is how to define a vector. If I want to define a matrix, matrix has to, for example, a 2 by 2, for example, a 2 by 2 matrix. Then I say, for example, here my variable is capital A is equal to 1, 2, 3. The first row is 1, 2, 3. And the second row, negative 2, 0, 5. Okay, then I create a matrix. This matrix, how many rows it has? It has 2 rows and 3 columns. 2 by 3 actually. This is 2 by 3 matrix. 2 rows and 3 columns. So if I want to, and it is available here in the workspace. So if I want to access, for example, what is this element? This element is the first row and the second element. So that means A1, 2. The first row and the second element. A1, 2 is 2. And what about this, the next element? This is 0. What about this element? 0. 0 is the second row and second column. So if I say A2 comma 2, second row, second column, A0. Okay. Another thing is to know the length and the size of a vector and the size of a matrix. As you see, for example, this vector A has how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements. Okay, A is 11 elements. So how I know the number of elements? By calling length of A. This is a command in MATLAB. Length of A is 11. That means it has 11 elements. What about for the matrix? For this matrix, A has 2 rows and 3 columns. Then I say size of A. Size of A will give me 2 rows. That means it is 2 by 3. 2 rows and 3 columns. Okay. This is how we do. And another is how we do matrix vector multiplication. For example, vector multiplication. If I have what is my A? My A is here from 0 to 100. So if I create another vector with so if A is start from 0, then 100, we have this with 10 steps, and B is from 1 until 11. I have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if I want to multiply A with B, I say C is equal to A times, okay, times B. So this, when I put point here, it means multiplication of element by element. So 0 multiplied by 1, 10 multiplied by 2, 20 multiplied by 3, 30 multiplied by 4, and so on. So I will get C. This is how you see 0 multiplied by 1, 0, 2 multiplied by 10, 20, 3 multiplied by 30 multiplied 20 multiplied by 360, 30 multiplied by 4, 120, and so on. So this is C. This is called element by element multiplication. Okay. So we'll have more examples like this. Now let's try to go to the first experiment that we started earlier. So this is a file, the sample file I already created. So I go to that sample file. Here is again omega naught 2 pi. T is 2 pi over omega naught. This is this part is the one where you write the script file. Okay, you can run this line by line from the command window here, but it is easier to put it in a script file. How we create script file? We just say here new, and then new, and then script file. This is new and script file. Then you will create here a new space will be created in MATLAB, and you write the script file here in this area, and you save it and you give it name. But I already did it, so that's why here I created this. Okay, by this way I created this, and then after that you save it, and there will be a file name for the script file. This is my file name, for example, lab1 v1. This is my file name, lab1 v1. Then I run it here in the command window. In the command window part, I run this. So let's see what is the result. Okay. First, I always clear the workspace before I run. So here lab 1 v1, lab 1 v1. So I run this. See, I got this figure. This is my figure graph. So as you see, this is a cosine wave here because I define my wave as sine wave, sorry, sine omega naught t plus theta. This is my example. And it has two periods. I plotted two periods. If you see here, I start from here and then come back. And how we determine the period? The period we determine by looking two similar identical points. For example, here I have maximum point here and I have another maximum point here. So the period is between this point and this point. Okay, in MATLAB, for example, I can locate this point. What is this point? Here, what we call it, we have here data. Data, if I click this, it means data cursor or data tip. So you will put a data cursor at this point. Okay, at this point, you see the x-axis is 0.12 means my x-axis is time and my y-axis is the signal amplitude. So the x-axis is 0.12 second and the y-axis is 9.995 approximately 10. Okay, so at this is my data tip or the data cursor, and I will have another data cursor. How? You right click and you say create new data tip and you go here, new data tip. You see? Now these 2 points are similar. How they are similar? Because the amplitude, if you see the amplitude, y is 10 here, approximately 10, y is 10. What about the time at this point? X 0.12 second. At this point, X 1.12 second. So what's the distance between these two? The distance between these two is 1.12 minus 0.12, which is equal to 1 second. So that means the period is 1 second. The period is 1 second. If we see from the function, it's 1 second actually. Why? Because my omega naught is 2 pi, 2 times pi here. And the period is 2 pi over omega naught. 2 pi divided by 2 pi is 1 second. And I have the time sample 0.01, of course, to create the signal. I use the time sample 0.01 and my theta is pi over 4. So I call x of t 10 times sine omega naught t plus theta t. 10 is the maximum. If you see, the signal will oscillate or swing between 10 and minus 10. Okay, 10 and minus 10 because it's sine signal. And then plot txt and grid on means make square grid like this. This is a square grid. And the x level is time, the y level is the signal amplitude. So we plot two periods of this. How we know that it's two periods? Because it starts here, if you see here, and goes and come back here, the same point, one period, and then another period, two period. So I plot two periods of this signal. Now, if I want to change the color, this is blue. So I can again go here and change when I call plot txt, for example, here red. R means red color. So plot in red color. If you see here, there is here star sign. Star sign means you are not, you haven't saved it. So you should save it. Save it. Then the star will go away, and then I again call the previous function. You can use the up arrow to bring the previous command. Okay, and from the keyboard, if you press the up arrow, then you will get the previous command. lab1v1. This is my script file. Then I run it. You see the color will become red color. Red color. And this is if I plot the whole figure. If I want to make two rows of this two rows with the same figure, I can plot another one, but I have to use another command called subplot. So here, after I define the time, I say his subplot. I make two rows, and one means in the first row, make two rows and one column for my figure. Okay, 2 rows, 1 column. And in the first row, you plot x of t. Okay, you will plot x of t. And in the second row, I can plot another signal. Okay, let me define the other signal. Okay, this the other signal, I can define it. I can define a second signal. Okay, and this signal, let me call it, let me call this the other signal, the other signal yt. Yt, I call it yt here. And let me give the amplitude 5. And let me change the signal to cosine. Okay, cosine subplot 211. Then in the first one we have this, and in the second plot we can plot again yt. So here I will have another one, subplot here, subplot 2, 2, the second 2, 1, the second row. In the second row, I will plot yt, and with a different color, yt, and for example, I can make here blue color. Okay, so I have two plots now. In the first row, I have xt, and in the second row, I have yt. So the signal amplitude, and then I save it, and I call again. If there is an error, he will tell me if I make a mistake. You see, now I have two rows here. And the first row, I plot x of t. And in the second row, the cosine signal yt. This is yt, time amplitude. By this way, you can make two rows. And for your exercise, you can, I ask you to do 3 rows, and you can do that. Okay. Now this is the first part of the exercise. Let's go to the second part. The second part is plotting exponential signals. Plotting exponential signals. How we define exponential signals? From the theoretical lecture, if you remember, x of t e to the power of alpha t, where alpha is a real parameter. Okay, so we define a vector of time using the MATLAB command from t, for example, 0, and the time step 0.01 until 6, and we plot these 3 different signals. x1t e to the power of alpha t, this, x2t, this, x3t, this. Plot on the same graph, use 3 different colors and give appropriate legend and xy level. On the same graph means on top of each other, okay, with different colors and xy levels. Okay, and here another question for you here. Plot x1t and x4 of t. Okay, x4 of t is this one on the same graph, and after you plot, discuss the difference between the two signals. Okay, now let's go to the sample. This is a sample MATLAB code. Clear all. My time step is 0.01, maximum time 5. I start from 0 until 5. And how we call exponential functions in MATLAB by using exp function. X of t to the power of exp minus 0.5 times t, and then plot t times xt. And then you make x level and y level. Okay, let's go to the example now. Here I already made a script file for that. This is the script file. Clear all, t sample 0.01, the maximum time 5. I start from 0 until t max, and I define here x of t 2 times exponential of minus 0.5 t, plot txt grid on x level time. So let's run this lab. The name of the file, as you see, is lab1v2. 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 Okay, so I run it. As you see, this is exponential signal. The x-axis is my time, the y-axis is the signal amplitude. And remember, at t equal to 0, what is the value? E to the power of 0. E to the power of 0 is 1. 1 times 2, 2. Because the signal is 2 times e raised to minus 0.5 times t. And if I want to, the value at t is equal to 1, here at t is equal to 1 is 1.2. I use my data cursor here. Remember this data cursor. And I locate this point. Approximately, you see, at 1 second, it's 1.02 second, for example, 1.2, and so on. So it is decaying function. Why? Because I have minus 0.5 t, minus 0.5 t, because I have here minus. Now, if I want to plot another signal here on the same graph, I can define the signal. Let me call that signal again. I define that signal as yt. Let me call it yt. And I call exponential of e raised to, for example, 0.8 t. Okay, so exponential of 0.8 t. Then here plot xt. Let me call this color is blue, for example, the first one. And on top of it, I want to plot, I use hold on command. Hold on means plot on, if I want to plot on the same graph. Okay, if I want to plot on the same graph, so first xt, now yt, and I give different color, for example, a red color, plotting yt, okay, as a function of t. Okay, then remember this star, it is we should save it. Okay, save. Okay, then we call the file name. You see, and now let's see the graph. You see, on the same graph, the blue color is the first one we plotted 2 times exponential of minus 0.5 t, and the other color, the red color, is yt exponential of 0.8 t. Then I can insert here legend. Legend means, you see, if I want to label the different graphs, legend, insert legend. Yes, here I can say, for example, the first graph is, I can give this name for the first one. You can say this is x of t, for example. And if you like x of t, this you can call it. And the second one, you can call it y of t. Okay. So by this way, the person will know which one you are referring to. Okay, by the different color. By the way, after you have done this, you can take all the results to Word. So, for example, I start to Word here, and we can take all the script file, the figures to Word. So I click here Word, and if I want here the script files, I just take here, okay, copy the script files here, then right click, copy, then I take it here, paste. Okay, that's when you do your lab report, that's what you will do. And if I want to take the figure, edit here, copy figure. Okay, copy figure, and then you copy here. That's it, and you save it. You save this document in any folder you want, and you write. This is actually, this is a script file. The figure is not copied. Again, edit, copy figure here, copy figure. Then Yeah, the figure is here now, and you can discuss the type of, by looking this you can make discussions in the Word file. You can tell about the difference between the two signals. For example, you can talk the value at time is equal to 0, at time at any time, and you can make so many discussions. So when you are plotting the signals, we want to see discussions from the students, because we want to know the students understand the concepts. That's why we want discussions. So please follow the submission guidelines when you make your own report. Then you can save this, and you can send me the Word file, and also you can print it and submit hard copy also. All right, so this is about the exponential signal. You can continue the rest. Now, the last part is harmonically related periodic signals. Remember, what is harmonic signals? Harmonic signal means I have one fundamental frequency in the signal, and I will have multiple of the fundamental frequency. So the overall signal is the sum of many frequencies, where each frequency is a multiple of the first frequency, or we call it the fundamental frequency. So that is a harmonically related signal. For example, here, this is a mathematical expression. R of t is from n, starting from 0 to n, Cn cosine of n omega naught t plus theta n. So I start from 0 until capital N. That means n plus 1 different types of signals. Okay. And when n is varying, the frequency of the signal is varying. Okay. When n is equal to 1 is the fundamental frequency. When n is equal to 2, the second harmonic. When n is equal to 3, the third harmonic, and so on. So this is a summation of many frequencies, where each frequency is a multiple of the fundamental frequency. Okay. Now, this Cn omega naught and my time sample are saved in a certain file. Okay, omega naught, Cn, and theta are saved in a certain file. So you should go and upload that file. Okay, upload to MATLAB command prompt command window. Okay, how you, by using the load command. The load command, we will see the examples below how it can be done. So this one normally we put it in the course material section in Blackboard, and there is a file which contains these parameters omega naught, Cn, theta. It's a MATLAB file, and the extension for that file is .mat. So here there is one file which is called R1 param. R1, that means the parameters of R1t for the signal. So the name of the file is R1 param.mat. What does it contain? It contains omega naught, Cn, theta, and t sample, sampling time. Okay? And then you load this to the command window, and then you plot the signal R1t. How many periods of that signal? 4 periods of that signal. Okay. Another parameters R2 param.mat. You load again this the parameters for this file, and then you make the signal R2t, and you plot 4 periods of the signal. The last is R3 param.mat. This is also a MATLAB file consisting of these parameters omega naught, C, and theta. And again, you load that, and then you call that file, and get the parameters, and you plot R3 of t versus t. How many periods? 2 periods. Okay, you must read these instructions and follow and try to work on this. Now, the last signal, R3 of T, it is called a sonar signal. It's a sonar signal, that means a sound signal used in submarine communications, underwater or undersea communications, okay, for submarine communication. So they used it for detecting, the signal is used for detecting of objects. So the signal is sent, for example, from the warship or the submarine, and underwater it is sent. And if there is an object detected, then the reflector signal will come back to the transmitter, and by this way they know that there is, for example, an enemy approaching the warship or the submarine. So it is used for submarine communication, and we call this signal sonar ping signal. Okay, so we can you can see that signal, you can plot it, and you can make the sound, can listen to the sound by using sound sc command. Now here I make a sample MATLAB code to plot all these signals. Okay, the only thing what you will do here for your case, here I created one file called xparam.mat. This is for my sample MATLAB file. So I have my parameters Cn, theta, and omega naught, and t sample, and I define the period 2 pi over omega naught, and then the maximum time I plot 2 times t, two periods plus 0.1 second, and the sample time 0.01. The sample time is actually it is saved here, already saved, no need again to call it here. And then we go from time 0 until t max. N is the length of Cn. That means how many harmonics I have. How many harmonics I have. X of t means the signal, the overall signal, x of t. Now, first I initialize here. The initialize is zeros, 1 until length of t. That means for all the time samples, initially it is initialized as 0. Then I create a loop here. So what this loop does, it will add each harmonic signal every time, okay, in the loop. So in the first case, when n is equal to small n equal to 1, I have x of t, the next value of x of t, the previous value of x of t, which is all are zeros for all time samples, plus the first harmonic, the first one, Cn1, the first harmonic, sine n omega naught t plus theta n. Small n is 1, that means I am calling the first harmonic signal. So in the first loop, the first harmonic signal is added. In the second loop, the second harmonic signal is added on top of the first harmonic signal. In the third loop, the third harmonic is added again. So 1, 2, 3, that means, and so on. So I finish all harmonics, I add them. Then finally, the final signal, when I finish the loop, this is called for loop. When I finish the loop, finally, I added all the harmonics. Then I plot t versus xt, and then I can label x label and y label. That way, I have this script file. Let's see now in MATLAB how this looks like. Okay, so I go. This file is here. You see, let's say so. Let me clear this part, all the previous variables. Okay, so I clear all and I load xparam.mat. Let me show you what does xparam.mat looks like. See, I call here in the command window. This is command load xparam.mat. What does here in the workspace? If you see, what does it contain? It contains Cn, theta n, t sample, omega naught. Okay, what is Cn? Let's see what Cn. Cn are simply amplitude. First harmonic amplitude 1, second 1.2, third 0.5, fourth 0.8, fifth 1.5. You see, I have 5 harmonics So this is the amplitude, okay? And theta for each harmonic, theta n, okay? Theta n, theta n. The first one, the phase angle, 0. The next one is minus 0 point, this is minus pi over 4. And this is pi over 2, and so on, okay? So until the fifth one. The t sample, what is my t sample? 0.01, already it is there, okay? Omega naught is 6.28, means 2 pi, okay? Omega naught, if I call it here omega naught, it is 6.2832, means 2 pi, okay? Now what will be the period if your omega naught is 2 pi? If I use this equation, T is 2 pi over omega naught. So omega naught is 6.283. So 2 pi over 2 pi is 1 second. So this signal, the fundamental period of the signal is, that means 1 second. Okay. Now after we do this, you see now T max here, then I have the time vector from 0 to T max and length, n length of Cn, and then I make this for loop as I described before, and after that I finish this, and this is the name of the file, lab1v3, lab1v3. Okay, let's see what is the graph. You see, this is the graph, the plot of the signal x of t. Okay, so here, for example, if I want to see the period, remember the period is between two maximum points. Here is the period. I make one data tip here, and another, I create another data tip, create new data tip here. You see, approximately here, between these two points, I have 0.29, 1.28. So if you subtract this, you get 1 second, the period 1 second. Okay, so by this way you can plot the graph. So if I see, for example, here, if I want to hear the sound SC, okay, what is my signal? X of t. See, you hear a certain sound again. This is the sound again. This is the sound of this signal. For your case, you have to change this load X param. This one, okay, it will be supplied in the course materials section. So the first parameter is R1 param dot mat for R1 of t, and R2 param dot mat for R2 of t, R3 param dot mat for R3 of t. So you change this, and you will find, and then you determine the signal. It's very easy actually. I made it for you easy here. The only thing is you change this load section, and you can plot the signal and look the signal, and you can talk about and discuss about the signals. Okay, that's all about this first part of the lab. Additional things, if you want to know about MATLAB, here there is, if you see this is question mark, this is called help. So if I click this help, and if I, for example, if I want help for any MATLAB command, I can ask in MATLAB. So a little slow actually, it's coming. Okay, so here the help window is coming here. In the help window, for example, if I want to know about plot, search plot. See, plot. It will give you plot different results. Is plot two-dimensional signal. Plot, how you call plot? Plot, then the x-axis, comma, the y-axis. So your x-axis is, for example, it can be time. Your y-axis can be x of t. Okay, this is how you call plot. Another plot XY, comma, line specification. That means the line color. Is it red? Is it blue? So in the line specification, you can put it in apostrophe. It can be blue, red, BR, and so on. Okay. But line specifications you can get here. You can refer different line specifications here. There are also examples. You can see how different examples are done. This is how different specifications here. Yellow, Y means yellow, for example, M magenta, R red, and so on. So any function you like, you can use the help function. For example, sine. And when I write sine, it came here. See, sine. Okay, y is equal to sine of x. Okay, so it will give you, for example, here x is from minus pi to pi, and plot x, which is from minus pi to pi, comma sine x. Read on. Then you have this plot. See this plot. You can exercise this. You can just take this copy and put it in the command window, or you can make a small script file. Okay, script file as I described here. Just make, for example, if I want to make this script file, let me take this part. I take here, copy, and I go to here, new, here untitled, then here, grid 1. Okay, so from minus pi to pi, remember. So I took it from the help section. Let me clear all. Okay, and this is untitled, yeah. So I will give a name for this. Okay, file, save as, sign. Let me call it. It should be different from sign name, because sign is a built-in function. So I give it sign 1. Just I saved it as sign 1. If there is any function which is sign 1, it will tell me actually. I don't have, so sign 1. Okay, this is sign 1. So let me call it here in the command window always. So this is my script file. I created it. So in the command window, sign 1. Let's see the figure. You see, this is sign 1, the one you have seen in the help section. You see, in the help section, this is it, sign 1. So the same. So by this way, you can use the help section to get any help regarding functions, regarding commands you would like to see. So MATLAB has a help section by itself, that means. Okay, so with this we complete the first lab, and remember to include all discussions and results and discussions, figures, and discussion is very important. Usually I check whether students understand about the concepts or not by looking the discussion part. It's critical. Do they really understand what they are doing? This is very important. So I look the discussion part when I correct the lab reports. So please discuss, and for what is required, you can follow the lab submission, report submission guideline, and also the lab manual. You can refer it. Thank you for listening to this lecture, and see you in the next lecture.